Okay. Good afternoon. Welcome to 139th episode of our Creative Online Weekend Talk. Weekend Talk, I am Supriya Nayaka, your host for today's talk. Creative. As many of you know, it's not just a group. It's a community of like-minded individuals fueled by curiosity and driven by the knowledge. Our name itself embodies our philosophy, creativity, and active, where we understand that to be truly active, we must be creativity in all its form. At Creative, our mission is simply yet profound, the fostering constructive thinking across various domains. That the sharing of knowledge is not additive but exponential. That's our tagline, Knowledge Square, symbolize the endless possibility that emerges when idea converges and minds collaborate. We are proud to announce that Creative successfully organizing weekend talks every Saturday from 3 to 4 p.m., being together curious minds from around the world to engage in thought-provoking discussion. Furthermore, for those unable to join us live, we extend our reach through live streaming on our YouTube channel, Creative GBD, ensuring that knowledge transcends geographical barrier and time zone. Today, we are honored to delve into topic that the topic that AstroSat UVIT, India's first space telescope with high resolution imaging capability. Our distinguished resource person, Mr. Prajwal Joseph, project scientist at the AstroSat UVIT Payload Operations Center, Indian Institute of Astrophysics, Bangalore, will be guiding us through this fascinating journey. But before we start the program, I want to express our heartfelt gratitude to all our resource persons who are generously sharing their expertise and insight with us, enriching our collective understanding. I welcome once again one and all for today's talk. Over to Joseph, sir.
Thank you. I'm very happy to give this talk. So without any delay, I'll start. Is my screen visible?
Yes, sir.
Okay, thank you. So today's talk is AstroSat UVIT. It is India's first space telescope with high resolution imaging capabilities. So you may have heard of AstroSat Observatory. If you have not, I'll be telling you about AstroSat as well as UVIT. I'm Prajwal Joseph. I'm working as a project scientist at the UVIT Payload Operations Center. We work in close collaboration with ISRO to manage the UVIT payload. You may be all knowing familiar with Srinath. We work together, and there are other people from ISRO also. We all work together so that UVIT data is accessible to scientific community across the world, and it is a very valuable data that is coming from this first Indian space telescope, and then it is being widely used. So I'll be telling you all about AstroSat UVIT. And as I said, it is India's first attempt, and it is very, I would say, very fortunate that we were able to be successful with our first attempt itself in building such a high quality space telescope. AstroSat is still there, still operational, and it is an amazing telescope. That image that you see in the background is taken by UVAT. So I'll be telling you more about that particular image. This image was taken by UVAT, and it is a part of a Whale Nebula. A Whale Nebula was a star before, but it went through a explosion called a supernova. And now what it remains of that star is only the hot gas that is left behind by that explosion of the star. And this particular structure in the sky extends actually 3 degrees in the sky. So when we talk about um, things in the sky, we talk in degrees. So the moon extends half a degree in the sky. So you can think that this particular object, Whale Nebula, the supernova remnant, extends almost 6 times in the sky. But you will not be able to see it through your eyes because your eyes are not capable of detecting the ultraviolet wavelength, because our eyes are only capable of detecting the visible channel uh, part of the electromagnetic spectrum. Now, this is a huge structure, as I said, but UVAT imaged only a part of it. So what you're seeing is a section of the Whale Nebula. I'll tell you about AstroSat mission. It was launched in 2015, 28 September. You can see the 3D model of the AstroSat observatory on your screen. There are 5 payloads on board the AstroSat observatory. They are UVAT, LAX-PC, SXT, CSAT-TI, and SSM. These are the 5 payloads. You can learn about each of these payloads through internet, but I'll be only talking about ultraviolet imaging telescope, which is UVAT. You can see the UVAT is marked in yellow. So it is a twin telescope. That is why you are seeing 2 tubes. So both tubes are 1-1 telescopes. These are twin. It is a UVAT is a twin telescope, and the AstroSat observatory is in a low Earth orbit. It is 650 kilometers from the Earth's surface. It is on a near equatorial orbit. And you should keep in mind that originally the expected lifetime of AstroSat was only 5 years. But even and 2015 it was launched. 5 years got passed in 2020, and it is still operational today. And coming September, it will be 9 years old. So that is a big achievement, going beyond the expected lifetime. Now you'll be wondering, how do you observe with AstroSat, this observatory that India has launched? It is being operated as an observatory where proposals are taken from all over the world um, through a web interface called AstroSat Proposal Processing System. And this proposal submission window is opened every year. Actually, yesterday was the last date for submitting AstroSat proposal. So many people across the world would have submitted AstroSat proposal yesterday. And the data from whatever is taken by AstroSat will become public after an initial proprietary period of 1 year. So anybody will be able to access the AstroSat data, including UVAT data, from the ISSDC AstroSat archive hosted by ISRO. Now I'll talk about UVAT, which is Ultraviolet Imaging Telescope. It is primarily an imaging instrument, and it can create images simultaneously in 3 channels: far ultraviolet or FUV, near ultraviolet or NUV, visible channel or VIS. The field of view is 28 arc-minute circle, and this you can again um, assume that it is close to the size of moon on the sky. The moon extends half a degree or 30 arc-minute length, and 28 arc-minute is very close to 30 arc-minute. So you can assume that the field of view of UVAT is close to the size of the moon in the sky. And the UVAT has a very high spatial resolution of 1.8 arc seconds. What did what do we mean by arc seconds? Because if two objects in the sky are only separated by 1.8 arc seconds, the UVAT in the UVAT image you'll be able to distinguish between these two objects. And to showcase the how good is the UVAT's imaging capabilities, I will show you an image comparison. So this is the image comparison. The what you see on your left is both show the same galaxy. Okay, maybe I should make that clear first. Both images are showing the NGC 300 galaxy, and it is a spiral galaxy. Now, the image on your left was taken by a telescope launched by NASA called GALEX. The GALEX telescope is not operational now, but it had similar capabilities to that which UVAT has. It also is capable of imaging in the far ultraviolet as well as near ultraviolet band of the electromagnetic spectrum. But it has a relatively poorer resolution than UVAT. So you can see the image resolution comparison here itself. You can see that there are more details visible in the UVAT image because it is a higher resolution image, because you can see sources which are nearby separated out, which you cannot see in the galaxy image. Now, more details about the UVAT telescope. There are filters available for selecting a band in each channel. For example, in the far ultraviolet band itself, um, scientists would like to observe in a particular band. There are various reasons for doing that. So there are filters available for selecting a band in each channel, and also a low resolution slitless spectroscopy is possible using UVAT with the help of gratings. And as I already said, it is a twin telescope, and each is having a primary mirror of 375 millimeter diameter. And the image that you're seeing was taken at ISRO during that is a fully integrated AstroSat uh, observatory, and there is a person standing nearby so that you can see how big the observatory is, AstroSat observatory is. The UVAT telescope, you can see, if you notice that there are the two twin tubes. You can see a tube at the front, which is SXT, and after that there are two tubes again, um, which is closed because it will only be open in the space. So presently it is closed. So that is UVAT sitting in the middle of AstroSat. And so it is a big satellite. So you can, as you can see. Now I'll talk about where I work. I work at UVAT Payload Operation Center, which is situated at Indian Institute of Astrophysics, Bangalore. Because UVAT was not built by one team alone. It was a collaborative effort. It was built by collaborative efforts from institutes such as Indian Institute of Astrophysics, TIFR, Tata Institute of Fundamental Research, IUCA, which is in Pune, and of course ISRO is part of it. Also, Canadian Space Agency is part of it. Canadian Space Agency provided the detector for the UVAT telescope. And the image shows a picture of Indian Institute of Astrophysics where the UVAT Payload Operation Center is situated. Now, what are the responsibilities and activities of UVAT Payload Operation Center? we routinely check the health of UVAT instrument, because UVAT can and it does get affected by cosmic ray hits from the outer space. So any the cosmic ray hits can damage, or I mean it can make the data go bad. I'll be talking in detail what do I mean by data going bad. So we keep on monitoring the UVAT's health, so that to identify if there is any problem with the data that is coming from UVAT. And if we detect any problems, we make measures to mitigate that problem. We will be asking for a reset of one of the channels, or if the problem is not going away due to some reason, we make corrections in the ground itself by writing software that can help mitigate that particular problem. And we process the science data that is available from UVAT, and then we make it available to the ISSDC AstroSat archive, so that it can be accessed by the scientists who have proposed it, as well as after the data proprietary period, it becomes publicly accessible, and everybody across the world can access it, and any scientist across the world can do scientific analysis and improve our understanding of the universe. And another responsibility is we develop software for monitoring, handling, and processing and analyzing the UVT data. That is a key responsibility. As I talk to you, we have been developing a new pipeline software for processing UVT data, which will improve many of the shortcomings the previous data release had. So we are constantly trying to improve the quality of UVT data. And as I already said, we detect and solve UVAT instrument problems as they arise. And we also support users of UVAT data. We develop tools for AstroSat proposal submission. Also, we advises and helps users with problems related to UVAT data analysis. So scientists or researchers or PhD students, scholars will come to us for help with uh, with any problem they face, or they seek our advice regarding how to analyze the UVT data, and then we support them. So this is what we mean by processing the UVT data. So if you look on the left on your monitor, you can see the unprocessed UVT data. So you can see certain patterns that are appearing. And on the right, you can see the processed UVT image, where you can see the beautiful Whale Nebula, a part of the Whale Nebula which I have shown. So this is the NUV channel data, if I remember correctly. And the patterns that you see in the unprocessed data, which I have marked unprocessed, is because UVT has a drift. The telescope is not very, the pointing does not remain stable. When you look at one particular part of the sky, it keeps on moving. So when you look at a particular part of the sky for maybe 30 minutes or so in a orbit of AstroSat, that particular movement of the telescope pointing causes that particular patterns to appear. So we need to correct for this telescope pointing drift, and only then you can get the processed image that you see on your right side. So this is what we mean by UVT data processing. Also, we make additional corrections, but this is a major aspect, major part of that processing. This correction of the telescope pointing drift, and get the beautiful UVT images that you see on your monitor. For another example is shown for the NGC 300 case. Again, you can see because of the telescope pointing being not stable, you can see how bad the unprocessed image looks with all that drift of the telescope. And after correction, you can see the beautiful galaxy that emerged. So this is what we mean by UVAT data processing. Now, this is a tool that we have developed to create light curves from UVAT data. The UVAT data can be also be used to study variable sources. There are stars that are varying in its brightness, and scientists study that variation in brightness to understand more about the star. Also, there are very massive black holes in the centers of galaxies called supermassive black holes. And recently, you may have heard in the news that uh, even Horizon Telescope team was directly imaged one of the supermassive black holes in a nearby galaxy. So, you might be aware of what are supermassive black holes. Otherwise, you can understand it as these are very huge black holes at the centers of galaxies, and when they accrete matter, when matter falls into this supermassive black holes or SMBX, they produce large amounts of energy, huge amounts of energy, and then they are called active galactic nucleus or AGN. So this AGN also undergoes shows a lot of hello, hello.
1 minute, sir. You can proceed, sir. You unmute you. Prajwal, sir, you are muted. Okay,
Am I
go
audible
ahead, sir.
now? Thank you.
Yes, sir. Yes.
So I was talking about active galactic nuclei, and then they also show lot of variability. And then scientists are using the UVAT data to study the variability of such astrophysical sources. And UV ultraviolet variability is a very valuable addition to their to understanding these sources and the physical nature of what are the physical processes that are involved in causing this variability and understanding the nature of these sources as well. So we have developed, the POC has developed tools for generating light curves. The image on your left is the logo of the software called Curvit, which can be used for generating light curves from the UVAT data, which is basically UV variability data. And what I'm showing you on the right side is such a variable source of a star which is varying in its ultraviolet brightness. So this is another thing that we have done as part of the UVAT payload operations activity. Now, UVAT has been observing for last 9 years, and it has observed many regions of the sky already. What I'm showing you here is the uh, full sky wherever UVAT has observed already. So UVAT has observed almost 2000 regions of the sky, and those blue dots in your screen marks wherever UVAT has observed already. And it will continue to gain more data. So I said that monitoring the UVAT payload is important, and I will tell you why. So if I have already told you about unprocessed and processed data, so this is unprocessed data where you can still see the drift. But in some cases, you will notice that certain things have gone wrong. So you because I have been looking at the UVAT data for so long, I can see that if something is not as expected, I will quickly flag it, and then we will uh, try to understand what is the problem and take necessary action to mitigate such problems in UVAT. And on the left, I'm showing a such particular bad case where the data was affected, and then we have to take necessary actions to correct the UVAT data by resetting one of the payloads. I mean, one of the channels. So after a reset, the data will become good, which is as expected, will contain only data without drift correction. So you can see that on the right side. So we are constantly monitoring the UVT data on the ground. So whenever a particular orbit data comes, we quickly monitor if there is any problem that are occurring, and this is being done for each and every AstroSat orbit data that comes to us. Now I'll show you some of the images that have been taken by the UVAT telescope. This is the M101 galaxy. It is a spiral galaxy. Recently, a supernova occurred in this galaxy, and UVAT data was used to study that particular supernova, which is an explosion of a star during its later stages of life. And this is the Helix Nebula, and it is also known as Cat's Eye Nebula. And as you can see, it resembles an eye in the sky. And this is also a supernova remnant, but it is much farther than the Whale Nebula, so you can you know encompass the whole of that particular nebula in the UVAT field of view of half a degree itself. Unlike the Whale Nebula, where because it is so close, we could only image section of it within the UVAT field of view. This is a nearby dwarf galaxy called Small Magellanic Cloud. So it is a satellite of our own Milky Way galaxy. And again, this is only a small section of the Small Magellanic Cloud because it is so close by. It cannot be. We will have to observe the Small Magellanic Clouds through multiple pointings because one point with UVAT field of view cannot be contained. So people who study the Small Magellanic Cloud use multiple pointings at different parts of the Small Magellanic Cloud to study this particular satellite galaxy of Milky Way, our own galaxy. Now, the scientific output. UVAT produces the most number of publications among the AstroSat payloads, and there has already been 200 publications using UVAT data so far, and more data is being acquired, and then continuously people are using it, and the number of publications are only going to grow in time, and the growth is almost exponential. So you can expect 1,000 publications in very little time. So this is a big achievement for one of the first attempt India has made in this respect. And so we hope that the UVT data becomes very useful to the scientific community, and it will provide a big boost in morale for the Indian scientists and as well as the uh, the people who are using the UVT data for their publications. I hope they continue to do it. This is the summary, and UVAT is valuable asset to the international scientific community, and the telescope remains operational even after 9 years. The UVT data is publicly available from ISSBC AstroSat archive. Thank you. I will now take questions, and we can have a discussion if anybody have any questions. Thank you.
Thank you, sir. I'll open for question session.
Okay.
Okay. Any questions? Yes, Venkat.
Hello, am I audible, ma'am?
Yes, Venkat. Go ahead.
Okay, so earlier in this presentation, you told about three image frequencies. Those are FUV, NUV, and VIS, if I'm not wrong.
Prajwal, sir, you are muted.
One second. Okay, my camera is just.
Not you, Venkat.
Okay, yeah, sure.
Okay.
Yes, please go ahead.
1 second, sir. Um, yeah. So, earlier you mentioned three frequencies: FUV, NUV, and VIS, if I'm not wrong.
Yes, the visible channel.
Right, sir. So, I wanted to ask, since we have such of these high UV frequencies, what are the effects are we doing on, say, are we doing this on, say, other types of uh, other types of things in space, whether not exactly life, but any anything present in space, whether that's the star or anything that comes out because of these high frequencies.
The you can assume you can okay. I'll make it very simple for you. You can think of UVAT as a camera. Okay, you have your you are using a phone camera,
Mm-hmm.
and then you already have a telescope sitting behind you, and then
Right.
assume that it takes images basically. Now what you see when you're using those telescope behind you, you are looking at stars in the sky from the ground using the your eye is the detector. And when you're taking a picture with a camera, what are you using? You're using the phone as a camera, and then there is a chip or CCD on the camera, I mean on the phone, which is uh, working as an eye, and then that eye converts that CCD chip converts into images, and then when you look at your phone, and then after taking a picture, you can see that image. When you look at it directly with your eye, you're seeing that image directly, and your eye itself is working as a camera. Now, that you are operating in a part of the electromagnetic spectrum called the visible part of the electromagnetic spectrum. That is what you can see. Okay, and that so visible part of the you can only see the visible part of the electromagnetic spectrum, but there is so much other frequencies which you cannot see, like ultraviolet band you cannot see at all. You cannot see it in infrared, you cannot see radio waves, you cannot see X-ray, you cannot see gamma rays, you cannot see microwave. So there is a huge wealth of information in other electromagnetic uh, part of the electromagnetic spectrum which you cannot see. So in Earth, for example, in order to get night vision, you use infrared cameras, and which is used by military and other purposes. And there are other devices also. For example, X-ray we use in medical purposes, and likewise there are for scientific reasons for observing the sky, for example galaxies or stars in different parts of the electromagnetic spectrum with cameras. Basically UVT is a big camera, only that it is highly capable than your average phone camera. It can observe in it has a large uh, primary mirror of 375 millimeter, so it can um, you know observe things in higher resolution. So it is basically a large camera, and then it takes images in the ultraviolet part of the spectrum, and then ultraviolet part is not, it will be blocked by the Earth's atmosphere. That is why we have to go to space. Likewise, X-rays are also not reaching the Earth. If they reach the Earth, we will all die because X-rays are harmful. UV light is harmful to the Earth. So now, if we go to space and take these images of astrophysical sources in ultraviolet, X-ray, and gamma ray or infrared. Infrared, for example, now JWST is there in the space right now, and Hubble Space Telescope is there, which is observing the optical band. So when scientists want to understand one particular astrophysical source, they use information from all these different types of telescopes, and then they use their knowledge. They know physics, and physics is applicable to the entire universe. And you they have we have certain theories about how universe works, certain theories about how the gravitational force, the electromagnetic force, and how light gets emitted and all that. And we test our theories, or we try to understand what is the nature of one particular source. These are the sort of things that we do with the telescope we have in space as well as in ground.
Okay, thank you, sir.
Any more questions?
Okay, I have a question. How many of you knew about AstroSat before this talk?
One question in chat box. You can check.
Okay. So the question is how to process the data gathered, name software to analyze data collected. So this varies from AstroSat payload to payload. So if you want to analyze the AstroSat data, you have to understand which data you want to use. If you want to use the UVT data, you have to look at the UVT related software, which you can understand by going to the UVT website. And then the software is listed there. Also, there are various scientific publications detailing how to analyze the UVT data. And for other instruments, you have to go to their respective websites and also look at the scientific publications that detail how to analyze the data. Oh, so I'm showing you images, of course. You might be thinking the we are not getting the data that way. Okay, these are not colorful images that you get directly. What you get is that you will get far ultraviolet image, near ultraviolet image, and visible channel we are not using for science because it is there are some calibration not available for it. So basically the purpose of UVIT is to observing far ultraviolet and near ultraviolet. So that images that I show in my talk was created by processing, combining these two bands. And so that is a pseudo color image. I'll call it a pseudo color image, and it is not how you actually will get the data. So you have to process it first.
Okay. Any more questions? I think no more questions.
Okay. Thank you. Thank you for
Thank you,
giving me
sir.
this
Thank you
opportunity.
for your time and your knowledge sharing. We are very happy to have you on Creative, sir. Thank you. Thank you, one and all, for joining.